All right, let's get started. Today, we're going to crack the code on a real GCSE physics question. Now, we're not just going to find the right answers. We're going to get inside the mind of an examiner to really understand how you get every single mark. This is how you master the exam itself.
So, here's our game plan. We're going to break down question 7 from an AQA higher tier paper piece by piece. We'll look at the question, and then we'll dive straight into the official mark scheme to see exactly what they're looking for. Let's do this. Okay, let's kick things off with the first part. It's pretty straightforward, really. This one's all about pulling a key term right out of your fundamental physics knowledge.
So here it is, a 1 marker. You see the cyclist, and the question asks you to name force A. That's the one pushing the bike forwards. Have a quick think. What's that force called?
And there it is. For one simple mark, the answer is just friction. That's the exact word the mark scheme wants. It's the friction between the tire and the road that actually propels the whole thing forward. Easy peasy.
Okay, on to the next part. Now, this is a classic. It's all about testing if you can pull the right data from a velocity time graph. This is a bread and butter skill in physics for sure.
The question wants the distance traveled during a certain part of the trip. So what's the golden rule for finding distance on a velocity time graph? You got it. It's the area underneath the line.
The mark scheme breaks this down beautifully. For your first mark, you find the area of that rectangular chunk, which is 108 meters. For the second mark, you get the area of the triangle, which is 54 meters. And now, for the third and final mark,
You just add those two together. 108 plus 54 gets you the final answer and all 3 marks, 162 meters. Now, what's really cool is how the mark scheme handles slip-ups. Even if you mess up one of the area calculations, you can still get that final mark for adding your 2 numbers correctly. It's called error carried forward, and knowing that can be a real lifesaver.
All right, we're shifting gears now, literally. We're moving away from graphs and into a more conceptual question about how forces create a turning effect in a bike's gears.
So, this question wants you to describe a sequence, a sort of chain reaction. Think about it. What happens when you push on the pedal, and how does that effect make its way to the back wheel?
And here's the 2-mark answer, straight from the horse's mouth, the mark scheme. Point 1, you have to say that the force on the pedal creates a moment. That's the key physics term for a turning effect, around the pedal axle. Point 2, you then have to connect that to the chain, explaining that this moment creates a force on the chain, which then acts on the back wheel.
Next up, a calculation. And what's really cool about this one is that the mark scheme actually gives you 2 different totally valid ways to get to the right answer. Okay, first thing to spot here is a classic exam trap. See how the distance is in kilometers? Before you do anything else, you have to convert that to meters. So 0.018 kilometers becomes 18 meters.
So, the most direct route is using this equation of motion. It links up all the variables we have. You just plug in the numbers, shuffle the equation around to get A by itself, and then solve.
And when you run the numbers, you get 0.16 meters per second squared. And bam, that's all 3 marks in the bag.
But hold on, that's not the only way to get there. And any good mark scheme knows that. This just shows how flexible physics problem solving can be. Let's check out the other method for grabbing those marks.
So here's the alternative path. First, you can work out how long the acceleration took, which turns out to be 15 seconds. Then, you just use a simpler equation for acceleration, change in velocity divided by time. And guess what? It gives you the exact same answer. Both ways are perfectly correct. Okay, this last part, this is the one where a lot of people tend to trip up if they're not careful. It's a chunky 4-mark question, and it's all about drawing a scale vector diagram. Precision is absolutely everything here. Right, so what have we got? We've got 2 forces at right angles to each other, 200 newtons going sideways and 75 newtons going up. Your job is to combine them into one single resultant force using a diagram and say which way it's pointing.
So how do you bag all 4 of those marks? Well, here's the breakdown. Mark 1, for drawing the 2 forces to the same scale. Mark 2, for drawing the resultant arrow correctly, connecting them tip to tail. Mark 3, for measuring the length of that resultant and turning it back into a force. And finally, Mark 4, for measuring the angle to show the direction.
And here we have it. This is what a perfect 4-mark diagram looks like. The scale is right, the resultant is in the right place, and both the magnitude, the size of the force, and the angle have been measured and written down.
But here's the really important bit. What if your drawing isn't perfect? Or what if you decide to calculate it instead? Well, this is vital. The mark scheme explicitly allows a precise answer calculated using Pythagoras.
It'll even accept an angle measured from the vertical instead of the horizontal, or a bearing. Knowing these alternatives can save your skin.
Okay, let's just pause and take a step back. After going through all of that, what was this one single question really testing?
I mean, think about it. It tested a massive range of skills. It went from simple recall of a word to analyzing a graph, explaining a physics concept, running calculations, and finally doing some precise technical drawing. It just shows you how much can be packed into a single higher-tier question.
So, what's the big takeaway from all of this? It's that understanding how you're being marked is every bit as important as knowing the physics. Seeing exactly where the marks are, knowing what alternative answers they'll accept, and showing you're working clearly, that's how you turn good knowledge into a great score. Thinking like an examiner, that's your secret weapon.